Good evening, and I'd like to talk tonight about circuits, Year 10 GCSE revision. We will be doing this season, 2023, October session. We'll be looking at 4 out of the 5 GCSE topics, looking at circuit electricity, domestic electricity, waves, and what's the other one? Generation of electricity. And me and my colleague James will be running these revision sessions together. Okay, let me start off by going through circuit electricity as a general revision. I'll share my window with you. And okay, so here we have circuits, and we'll have a look at how these circuits work, and looking at what we've got in front of us, we can see that this symbol here is a battery. It's a single cell with a positive part and a negative part. And this sends current all the way around the circuit, leaving the positive all the way around. Doesn't go through the battery, it goes around the circuit, through the bulb in this case, and all the way around to the negative side of the battery. We've got also in our circuit a bulb which will light up when the current is enough and there are enough cells in the circuit. And so we have to look at our terminology here. So current is the rate of flow of charge. At a very simple level, we can say it's a flow of electricity. We can say it's a flow of electrons, but it's a little bit more than that. It's how quickly those electrons, the charge, flows around the circuit, the charge being the electrons. And we measure current, we can give it a symbol I, and we measure it in amps. So that if we wanted to measure it in the circuit, then we add in an ammeter. We have to break the circuit and we'll place an ammeter in the circuit, and that can measure the current going through the ammeter. Whereas when we're looking at this term called voltage, or there's another word for it called potential difference. Potential difference. This is in contrast to the current. It's the push required to get the current flowing in the first place. And this is measured, we'll give it a symbol V. It's measured in volts. And we use a voltmeter to measure how much push, if you like, an electrical push is given to the charge to make it move around the circuit. And we could put, for example, when we put a voltmeter into the circuit, we're always going to put it into parallel. All right, so we put it, the voltmeter always has kind of like 2 feet, one either side of the device. It could be below it, it could be above it. So I'm going to put mine below it, not to kind of get too crowded here. And you'll see that I put a voltmeter in that measures across the cell, and I put a voltmeter that measures across the battery. And what this is doing is measuring the potential on either side of the device, and it measures that difference in potential. And the voltage is, I can call it an electrical push. it's a little bit more than that. But that's a good kind of like analogy to compare it with current, which is the flow of the charge around the circuit, whereas the voltage is the push needed to get it around the circuit in the first place. So you've got, if we look, we've got another terminology, and that's resistance in the circuit that you need to be familiar with. There will be another one later, which is power. But we'll deal with resistance first. Resistance is the obstruction to the flow of the current. How much push do you need to get that current through the device? The more resistance something has, the more difficult it is to get that current through. And I like to kind of like liken it to an analogy of an obstacle course. So if you are doing an obstacle course, you're the current, you are trying to get through the obstacle course, and if there's a lot of things in the way of you, that is the resistance that slows you down. And it does a similar thing to the charge going around the circuit. It slows the charge down. So the more resistance in the circuit, then there's going to be a smaller amount of current flowing for that given voltage. So let's have a look at this in terms of what effect. So and resistance is measured in ohms, R in ohms, and it's got this special little symbol, ohms, omega, and we can say resistance to current flowing. So you've got two things in that circuit that affect the current. So if you give something, the charge, more push, more voltage, then you're going to expect that the voltage is, the bigger the voltage, the bigger the current. So if the voltage increases, the current increases. All right. So if you've got more push, you expect to see more current. However, if you've got more resistance in the circuit, you expect to see less current flowing, because resistance is the obstruction to the flow of the current. And if you've got more resistance in the circuit, there's going to be less current flowing. So if you kind of like look at this in terms of a way of relating current to resistance and voltage, then clearly the voltage and the current needs to be on the, and the voltage and the current, they need to be kind of like they're directly proportional. If you double one, you'll double the other. So the voltage needs to be on top if you're kind of like determining what the current is. But if you double the resistance, the current will halve. So you expect the resistance to kind of like be on the bottom of a dividing equation. So we say that the current is proportional to the voltage, but inversely proportional to the resistance. So what we have here is an equation that kind of like describes how current is affected in the circuit. And if we put that into our triangle, we've got the voltage on top. So V is on top. We can remember this because there's a little V, already on the triangle at the top, V upside down, and current and resistance on the bottom. So that our first equation, if we cover up the current with your finger, you're left with current equals voltage divided by resistance. And if you cover up now resistance, you're left with voltage is divided by current. And if we have an equation now, third equation, so that's one equation, two equations, and then the third equation would be that the voltage is equal to current times resistance. So we've got three equations from that, And I have to say, kind of like school books kind of like push this relationship, i.e. resistance is the ratio of the voltage to the current. But it's a nice way to look at it in terms of what effect the resistance and voltage has on the current, and you can remember it that way. Okay, I call this my Ver tree, okay, to try and get people to remember. And then from that, you can get all three equations. Now, that's not going to get you any marks, being able to remember that triangle. What gets you marks is being able to remember the three equations that stem from it, and being able to manipulate it so that you can get any one of those three equations when you need it. So moving on, let's have a look at these two bulbs now. And I've got more than one cell here. I've got 3 cells. Now I've got myself a switch into the circuit, and we have a parallel circuit. And things start to kind of like go a little bit odd. The current is still leaving the positive of the battery, the long side, and it's still kind of coming back into the negative, the short fat line on the other side. But how it goes around the circuit is that it gets to a junction here, and this is how you need to look at current, the flow of charge, or the rate of flow of charge, and then at that junction it splits, so that half will go in one direction and half, well, not necessarily half, it just depends on the resistance of the bulb A and B. But let's assume here that the two resistances are identical. If they are identical, then the current I2 and I3 will be exactly the same, even though it looks to you that it's taking a longer route going through B because there's more wires. Actually, we say that those wires have got no resistance at all. It's only bulb A and bulb B itself that has a resistance. So it doesn't matter how long the wires are, it's going to be 0 resistance in those wires. So we can say, for example, if there's 0.5 amps that flows out of the battery, and if the resistances of the two bulbs are identical, then 0.25 amps will flow through bulb A, and 0.25 will, so it splits up at the junction, will flow through bulb B. And this, interestingly, doesn't change. So you have 0.25 going into bulb A and 0.25 amps going out of bulb A, because it's not the current that gets used up in a circuit. It's the energy from the battery of the cells, which has got chemical energy, which is converted to electrical energy, which gets turned to heat and light energy. It's the energy that gets used up, and the current is carrying that energy. So it's like a coal man leaving a coal yard. He doesn't get used up. It's the coal on his back that offloads. That's the energy that gets used up, not the actual coal man himself. So liken the current to the coal man. The coal on his back is the energy that he carries. And it's similar here. It's the energy that goes around the circuit that is being used up in the bulb, not the current. So we've got the same amount of current before the bulbs as after. And then when it gets to a junction again, that current joins back up, all right, 0.5 amps back to the battery. And this is provided that the switch is closed at all so that the current can flow, because otherwise there's not a complete circuit and the current won't be able to flow at all. So I ought to kind of like go backwards a little bit and just, kind of like make sure you're clear with this. If 1 amp leaves the battery, the cell, in this case, there'll be 1 amp on this reading of the ammeter. There'll be 1 amp before and after the bulb. And even if I put another ammeter on the other side of the bulb, it will still read 1 amp going back into the cell. Okay, all right, moving on then. Okay, so that a parallel circuit will reduce the current in the branches. So for example, if I had 3 branches or 3 bulbs there, it'll reduce it by 0.5 divided by 3 in each branch, provided all the bulbs were identical. And it all depends on the resistance. And you can work this out because you know V equals I times R. So the voltage across both bulbs will be identical, but the current will change depending on the resistance. So if the resistance is higher, then the current's going to say, no, I don't want to go down that branch. So it will be less. All right. But the voltage across each will be the same. And I'll go over that in a little while now. Okay, so moving on, let's have a look at resistors in series and in parallel. Now, resistors in series and in parallel, we have R1, we have R2. R1 plus R2 in a series circuit like this is equal to R total, the total resistance of the circuit. So that even though we've kind of increased the resistance in our circuit, yes, the current will be less in the circuit. So instead of, say, 1 amp, and because it's got to get through twice as much resistance, it's got to go through twice as many obstacle courses within my circuit. So if I say, so that's 0.5 amps here and 0.5 amps all the way through, you can see that the current's got nowhere to go other than through the 2 resistors. So that all stays at 0.5 amps. There's no branches to split up, and it's quite nice and easy in a series circuit that the current stays the same all around the circuit. It won't be the same as if there was just one resistor, because there's double the amount of resistance in this case, say, so therefore the current will be less overall. But the amount of current going around the circuit in that particular circuit will stay the same. But now look at it in terms of the voltage. In terms of the voltage, which is the push required to get the current going through the resistors, it looks slightly differently to the current. We have to say is the voltage across the resistors. So if I show you that all of this side is connected to the positive, all right, and that's set at, for example, 3 volts, let's have 3 volts. And then the other side of the battery is kind of, or the cell in this case, is connected to the 0 volts. So all of this end is 0 potential difference, or 0 potential, or 0 voltage. Then you can see that between the black and the red is 3 volts. So between this black and this red is 3 volts. And the question is, though, what is the voltage, across any one of those resistors? Well, we're probably going to have to introduce another color. All right, so if I introduce another color there in between the 2 resistors, and let's say in this particular case, the resistances are identical, then the resistance R1 has a voltage which is between the purple in the middle and the black, whereas the resistance R2 is between the purple and the black. So because these resistors are identical, the voltage splits. No, I can't say splits, it's shared evenly. We know that there's 3 volts across both of them, so it's going to be 1.5 volts across one of them, 1.5 volts across another one. So between the black and the purple is going to be set at 1.5 volts. Between the black and the purple is going to be 1.5 volts. And between the 1.5 volts and the 3 volts is again 1.5 volts. Now, of course, this just depends on the size of the resistances, and that the amount of voltage could change if the resistance values are not the same. Okay, but if they are the same, then the voltage gets shared evenly. It's much easier if I'll put here the voltage shared. And this is in a series circuit, right? Whereas in a parallel circuit, it's actually much easier when we look at it in terms of the voltage. It's harder when you look at the current. So we've just looked at parallel current before, and we know that the current splits. It splits at the junctions here, and then it regains at the next junction. It kind of like reforms, it reconnects at the next junction when it's going back up to the cell. And we saw that in the previous part. But if I show you kind of like in terms of what the voltage is doing, this is all set at 3 volts here, okay, on this side where it's positive. On the other side, it's all set at 0 volts. Okay, so this is 0 volts on this side, and this is 3 volts on this side. And what the voltmeter is doing is sensing the difference between the 0, the negative side, and the positive, the 3 volts. So all of this side is set at 3 volts, 3 volts, 3 volts, 3 volts. And all of this side is set at 0 volts, 0 volts, 0 volts, and 0 volts. Now you can see that it's so much easier, because if you have a voltmeter across the black and the red, it's 3 volts. So the electrical kind of like push required to get that current flowing is 3 volts. And you can see that we've got the same here and to both of, so that would be 3 volts and that will be set at 3 volts, because you've got one bit of the voltmeter into the high potential 3 volts, and you've got one end of the voltmeter into the 0 volts. All right. So actually what happens is that the voltage stays the same in a parallel circuit. Okay, so that's what you've got to remember. In a series circuit, the current is the thing that stays the same, because there's nowhere else for the current to go, but the voltage is shared between whatever's in the circuit. Whereas in a parallel circuit, it's the current that gets split at the junction or recombines at another junction, but the voltage stays the same. Let's have a look at this kind of like idea of resistors in a little bit more detail. Now, you can have resistors that are not just fixed resistors. We can have resistors that kind of vary. So you've got the symbol of a resistor, and you can change it in a circuit by using an arrow going through it to show that it's not fixed, but we can change the value of it in a circuit. And that kind of like helps us when we put a variable resistor in a circuit. If I put it in my top circuit up here at the beginning, if I put one here, then what I can do is I can get a range of readings as opposed to just having one reading of current and voltage. All right, without that fixed resistor, there is another way of doing it, and you could add more cells, and you could put an arrow going through the power supply, or you could have a low voltage power supply. You'd have to have more than one cell, like a battery, in order to put an arrow going through it in order to be able to change it. But the idea of having either a variable power supply or a variable resistor in your circuit is you can get a range of readings, which leads on then to being able to plot a graph so that you can analyze the data more effectively, and you're not reliant on just one reading of voltage and one reading of current. And also, these things can change as the voltage changes. Okay, so thermistors are special resistors. The symbol for a thermistor is still a rectangular box. Don't draw the line all the way through it. If you did, that would become a fuse, which is a different, and I'll go over that in domestic electricity, but not here. And a thermistor is a symbol, is diagonal line, but not with an arrow, with a kind of like a little flat bit at the end. Now, the resistance of this changes with temperature, and it's really useful to use as a thermostat in our heating of water, so that our water doesn't all boil away, or it stops at a certain temperature, or the oven so that it stops at a certain temperature that it says recorded on the oven, and it doesn't kind of like carry away with itself. Okay, so we can use it in, we use thermostats quite a lot in our houses, for example, regulating the central heating system. And what happens with the resistance of a thermistor is, as the temperature increases, the resistance drops. Okay, so you can see this, and it's one of the few graphs where we can say that as the temperature increases, the resistance, so as the temperature increases, the resistance decreases, but at a decreasing rate. And what do I mean by that? It's just a way of kind of explaining how graphs work, really. And so if you have a fixed kind of like temperature range, you can see that the drop in resistance is quite marked at the beginning, at the low temperatures, but then for the same kind of like increase in temperature, you have a smaller drop each time. So now I've got this, I'm trying to get the same kind of like interval along my temperature, but the drop in is getting smaller and smaller and smaller, so that the drop decreases as the temperature increases. And okay, so these are little examples of thermistors. And moving on to light dependent resistors. Light dependent resistors, commonly known as LDRs, are, and this the symbol for LDRs is a light dependent resistors is a resistor, but with lines with the connections, contacts, and then we have two arrows going diagonally onto the resistor, and that changes the resistance with light intensity. So again, as the light intensity increases, the resistance kind of drops. So as light intensity increases, the resistance drops, and we can say again at a decreasing rate. Really, to get your kind of like second mark when they ask you to explain a graph like this, we ought to be putting at higher light intensities. Okay. And that will kind of like nail it. It's not good enough just to say as light intensity increases, resistance decreases, because it could be linear or non-linear. And it's not good enough just to say non-linear. You're better off saying that at a, at higher light intensities, the rate of drop is lower. Okay, all right. So where do we use these? Well, you see them in action on street lights. So when the light intensity kind of like drops to a certain level, it triggers a switch to switch on the street light. And it's got a clever use of a NOT gate in order to kind of like revert the natural way that LDRs work. Okay, so power now in a circuit. Power is measured in watts, given by a symbol P, and watts is in W. And we need now, if we increase the current in the circuit, so as current increases, then the power will increase. And if we increase the voltage in the circuit, then again, the power will increase. And you can see this by connecting more cells to the circuit so that you've got more voltage in the circuit, and the lamp will brighten up. Where if you turn up your power supply to get more current in the circuit, the power and the brightness of the bulb will light up more. So power is given by current times by voltage, and that is one of our equations. Power equals current times by voltage. All right, so if we increase the current, you increase the power. If you increase the voltage, you also increase the power. Okay, I'll get rid of those though for now. Don't think you need those. Okay, right. Now that's one equation. So let's just get rearranged to get the other equations. So current, put your finger over the current, and current equals power divided by voltage. And then lastly, the voltage equals, put your finger over the voltage, power divided by current. You have to be able to do that. I call that my PIV tree. Okay, to try and remember it, my VER tree and my PIV tree. Okay, so moving on, we've got a little bit of time for some problems. I just want to go back though, just to kind of like recap. If you had this particular circuit here and you didn't have a branch to it, then the bulb would be much brighter. By putting things in parallel, you're splitting up the current at the junctions, so there's less current going into the bulbs. The voltage will stay the same in a parallel circuit, but because there's less current, that means that these bulbs will be a lot dimmer than if they were, just one bulb in parallel with the cells. Okay, so that's the effect of having a parallel circuit. Having said that, in a parallel circuit, if one of those bulbs breaks, the other one still works. So it's likely that the lights in your classroom will be set in parallel so that if one of them goes off, all of the rest of them will stay on. It's no good putting it in series circuit because the voltage that's supplied to them will be shared between the number of bulbs that there are, and if one of them broke, they would all not come on, because you need a full circuit and no breaks in that circuit for the bulbs to work in a series circuit. But not so with a parallel circuit. Parallel circuit, one of them could break and the rest could stay on. So that's the advantage of having a parallel circuit. So when you buy your Christmas lights for your tree, then make sure that they are parallel and not series. Otherwise, you have to look through all of the bulbs and you have to test each of the bulbs to see which one's broken and replace it. Okay, so let's finish off with an example of a question, a graphical question. And the student has been asked to plot the graph. First of all, though, we've got to set the scales. Now we've got the voltage up to 12 volts given to us. We can see that the current is given to up to 3. So we can go 0. Now we could go 1, 2, 3, and lots of my pupils will do that. But it's not using the whole graph grid. So have a look at that. You know that you want to go up to 3, but you want to use the whole graph grid. So my suggestion is you will go 1, 1, 2, and 3. And you can mark each square still by going halfway in between. So 0.5, 1.5, and 2.5. And a lot of my pupils will forget the 0 at the start. And WJC seem to be a little bit picky on this. So you really do need to remember, if it's going to start at 0, you put the 0 in. You don't have to start it at 0 every time. You might want to start it with another number. But the point is, you can still read off from that very, very bottom point. Okay, so let's be plotting these. So there is a plot at 0, 0. Be mindful to remember it. Again, 0, 0's in the table. Every table reading, there has to be a plot on the graph. Okay, 1, 0.5. Okay, 2 to 1. 3.4 to 1.5. So 3.4 is here to 1.5 is there. 4.5, now it goes 4, 5, 6. So 4.5 will be halfway. A tricky one to remember. Okay, so that would be more like there. 8.1 is half a small square, and that would be 2.5. And then finally 11.8, so 10, 11, 12. So 11.8 will be that last little square right at the top. All right, and it asks us to plot the graph. Now, it doesn't say to draw, use the grid to draw a graph. So it doesn't say to join that line of best fit, but it is assumed that you know to do that. Now, looking at that, it looks to me like it's going to be a curved trend, but one of those points might be slightly off. So we're going to give it a go. We're going to give it a go. Just start at the 0. Just look ahead at the next one. Keep going, keep going. You just have to have a little bit of confidence and a little bit of practice on this. And you'll see that one of them is not quite right. You do not try and include him in your line. Don't want any kinked lines, okay, or joined lines or anything. One smooth curve with a sharp pencil, trying to go through the majority of points, but it's you can have an even distribution of points either side of the line, but you can see here that there's one point that's going to be off. So another student suggests that each reading should be repeated at least twice more to assess the repeatability. Well, I think in this case it is necessary because there's 1 point off the grid. So 1 point off, I don't mean off the grid, I mean off the line of best fit. So actually it would be a good idea to repeat results. And then you see, if you repeated results, you could ignore any anomalous or take out any anomalous results. You could see, you could do it again, as long as you've got 2 similar results close together to see which one you should chuck out. It would be a good idea to repeat another couple of times, and then you can see if there are any anomalies, you can kind of disregard them so that you have, in effect, a more accurate set of readings that you can plot and assess where the line should go. Now, next part, describe, there are more ways of getting those marks. For example, if you repeated, you would get a more accurate mean result. And that's what WJC are looking for. You can't just say a more accurate set of results. You've got to say, what is it that's going to be more accurate? And in this case, it will be the mean value will be more accurate. The mean current, since that's what we're repeating, would be more accurate. And so hopefully you'd find it closer to the line of best fit. Describe carefully how the resistance of the lamp changes as the voltage increases from 0 to 11.8. Well, this is really tricky because you haven't actually worked out any resistances, and nor have you plotted any resistances. So you know that resistance is equal to voltage divided by current. So let's just do it in a couple of places. All right, it says from 0 to 11.8 volts. If we did it here, the resistance is going to be 2 divided by 1 equals 2 ohms. Okay, right, let's take it in another place, say further up here. Okay, at this point here. We're not taking the gradient or anything. We're just looking at what resistance values would be. And I'm choosing, I ought to do it every, kind of like every 2 volts to see how it changes. But I'm going to just jump up to this one, 2.6 divided by 10 divided by 2.6. Yeah, 10 divided by 2.6, which is roughly, without using a calculator, is roughly 4 ohms. So the resistance is changing. Okay, and it is asking how that resistance changes. So you can say as, and they're asking as the voltage changes. So as the voltage increases, the resistance increases. Now, I think really to get your second mark, you need to say how it increases. Does it increase at a decreasing rate or at an increasing rate, or a decreasing rate? And the way to do this really is to work out the resistance at every kind of like point. Now you can do it according to the points in your table, but I wouldn't. I would use the points that you know on your graph. So for example, work out here, that would be 1.65. So that would be 4 divided by 1.65. Here would be 6 divided by 2.1. Here would be 8 divided by 2.5, let's just say. And you can get a value for the resistance at regular intervals along the graph and see how the resistance is changing. A lot of work for those 2 marks. Okay, moving on. The student, I think I ought to finish it here. I just finished this one and then I will stop. Okay, a student is making a 40-watt light source for a model theatre and decides to use a pair of these identical lamps in parallel as shown below. She adjusts the power supply so that the ammeter reads 5 amps. So with 5 amps, look, it's a parallel circuit. So half will go here because you've been told that the lamps are the same, and 2.5 amps goes here. So if we use the graph at 2.5 amps, the voltage is 8 volts. Okay, so from graph 2.5 amps goes to 8 volts. So if we wanted the power of one of the bulbs, that's current times by voltage, equals 8 times 2.5, which is 1620 watts. But now we've got 2 bulbs, so we go 2 times 20 watts equals 40 watts, roughly. Okay, so there we have it. You can go over it in a little bit more detail, kind of like slower, and rewind it. But basically, that is kind of like a standard GCSE question of plotting a graph and getting data from the graph to put into this equation, power equals current times voltage, or you could have the Ver one, voltage equals current times resistance. We've looked at resistors, like dependent resistors and thermistors. We've looked at kind of resistors in series and in parallels and the effect of current and voltage on them. And we've gone over the Ver tree, and you can combine the Ver tree and the PIV tree to get a new set of equations. Power equals I squared R and power equals V squared upon R. And that is kind of like another level again, a higher level again. And we went over kind of definitions of current, voltage and resistance. And I hope that that has now helped you in your revision for circuits. My colleague next time is going to do generation of electricity, and that will be on next time. Okay, session number 2 in the series of 4. So I'm going to stop sharing now, and I'm going to stop recording and say goodnight to you. Goodbye.